Now that we know what the PID controller is, we can look at the second step. We can see how we can tune a PID controller. So first of all, what is the PID controller? It is a control law. That's it. That here is the control law, which says that the output of the controller is a function of the error, the integral of the error, and the derivative of the error. Okay. And we can see that we have three parameters we can choose. We have our controller gain k. We must select. We have the integral or reset time, and this is a time. This is why it's 1 over ti, because in this way ti is a time. And we have the derivative time, td. In German die Nachstellzeit und die Vorhaltezeit. Now, so the bad news I have to give from you from the outset, there are no optimal tuning parameters that work for all processes. You probably have guessed that. So I can't tell you choose k equals to 1 and ti to 10 and choose td to be 2. The reason why this doesn't work is twofold. So the tuning settings, when I say tuning settings, I mean the choice of k, ti, and td, depend on two factors. One, they depend on the process dynamics. One. And secondly, they depend on the performance, the control performance requirements. What do I mean by control performance requirements? If you remember from the last video, we looked at disturbance rejection. How do we deal with load disturbances? So we have a blue, set points are always blue. I don't know if you knew this. Oh, this doesn't work. Our set points is always blue. We have a constant set point R. And if a disturbance hits our process, we are probably going to see that, but the PID controller is going to make sure it's going to go back to its original value. And obviously, we would like to see no impact of the disturbance on the process variable y. But when we do, which we will, we call this the speed of response. And we call the change in amplitude of the process variable, we call that robustness. And the two are connected. Usually when I have a faster process, the result is that my robustness goes out of the window. So we'll have a longer or a higher change in amplitude. And I have to balance the two. So it's speed versus robustness. Okay. Generally, we can say the following. And this is quite useful to think about that. We have our tuning parameters. Which are, okay, oh, this doesn't work. Let me try another pen. Got loads here, all don't work perfectly. We have K, we have TI, and we have TD. And we can generally say that the impact of K on the speed and the robustness is as follows. If we increase K, the speed will increase. So that means we choose a higher value of K, our response here will be faster at the expense of the robustness. Okay. If we increase our reset time, Ti, what's going to happen to the speed? The speed is going to go down. And that makes sense because if I have more Ti, that means it's inversely proportional here at this point. So it's going to be less integral action. So if you have less integral action, the speed will go down. On the plus side, the robustness will increase. I could have written, if I increase the I part, then I would have written here 1 over Ti, then the errors would have been just like for the proportional part. So now the derivative action, and I hope this is going to motivate everyone to use the D part of a PID controller. The derivative action improves both speed and robustness. It has the capability of doing both, improving the speed of response and the robustness. If you saw the images, which was hopefully pretty lifelike in the previous video, you saw that we really got a much better response, and it was both faster and there was the peak was less. Okay, so now you can say, why don't I always use the derivative part, and why don't you use as much as possible of it? So the answer is, this comes here with a little caveat. So this only works up to a certain point. This is only for small values of TD. This is only true then. And above a certain point, my robustness goes out of the window for small values of TD. And I could say I've written the notes up to a point. Okay, so now we have, and now I think I can brave a new color. We have model-based tuning methods. So these model-based tuning methods are in very many cases based on a step-response experiment. And the step-response experiment of many of the processes we see in the process industry looks like that. So this is our process variable as there's a step coming here at time equals to 0, at t equals to 0. I put a step on my process input, and I observe what happens to my process variable, and I can see it changes accordingly. And this is a super common response in the process industry, for chemical processes, for many of our natural occurring processes. This is what's going to happen. So now we approximate this response, the higher order response process, or the higher order process, with a first order process plus dead time. So now you have to remember what we learned about first order processes transfer function. So the transfer function of this approximated process will be equal to g of s equals to a first order process function kp divided by tau s plus 1 times e to the minus s. And then I like to use the letter L, which indicates the dead time. And I apologize for the confusion, but I'm going to call this a capital T, and this is a capital L. So now we have 3 model parameters. So we have 3 controller parameters, and just to be on the equal side, we have the process model parameters. I'm going to call them process parameters. And these 3 parameters are KP, they are L, and there are T. How do I read that out? Well, I read it out by fixing a first order process model here, first order here. This is not working very well. Here, this is the first approximate, this was the first order process plus a dead time. Yeah. So I have the dead time. And again, I apologize if you know this as something else, or we've done this as another parameter. We're going to call it L for the time being. And then I have the 63% threshold. 63% of my final value gives me the time constant T. So Kp is the process gain. And I should write this yellow because this is actually my yellow process model. The response is a higher order, actually a higher order process model, but my process model is yellow, and it has the process gain. It has the dead time L. So this is the time when nothing happens. I have to wait for a bit. And we have a time constant T. The time constant of the first order process. Okay, so now there are many tuning rules that are effectively lookup tables where you can figure out what KTI and TD is based on the process model. And you could have a different process model. The most common process model is this one here, first order process plus data, but you could have a different one. For integrating processes, this doesn't work. So when I say there are many, I mean there are like thousands. There are not like, there are thousands of tuning rules that we could choose from. And the reason why we have so many is, again, because we have different process dynamics and we have different control performance requirements. We have different process models. So there's room for many. And remember, control systems is not only for biochemical and processes and chemical processes. Another process we encounter in the process industry is also for helicopters, for drone control, for robotics control, for automotive control, for all sorts of control application where we want to keep a constant a process variable fixed. So it's not necessary for us. But for us in the process industry, we are recommending the following tuning rules. One is called AMIGO, and the other tuning rule is called Lambda. Arguably the most famous tuning rule is called Ziegler-Nichols tuning rule, and that is not appropriate for the process industry because they have optimized the tuning for a disturbance reduction in robustness of 25%. That means I am allowed to have an undershoot here of 25%, and that is not acceptable if you're controlling a pressure or a temperature in the process industry, which are very restricted. So I do not want to have overshoots for us in the process industry. So these two tuning rules are advisable in the process industries. There are others that are recommended. For example, in the Siemens user manual of a Siemens PID controller for the process control system, you will find a tuning rule that is called, is by Tien, Roens, and Resnick. It's from the 1950s. It's popular in very many areas. Some claim it's less superior, but it's still being used. And another one is called SimC. This is a very recent method by a Norwegian process control engineer called Sigurd Skogestad. And there are many others that you may want to choose. So I am going to give you AMIGO and Lambda because I do think they are very good. Okay, so here we go. I'm going to give them to you for you to have a look at and to understand what it looks like. So first of all, we have different tuning rules depending on whether we're going to choose a PI controller. Whoa, I've got flying pen caps here now. Alright, so whether it's I have the AMIGO tuning rules for K and TI for the case that I have a PI controller. So if I have a PI controller, I only have K and PI. And now I have to write it up. So the most important thing is that most tuning rules have the factor 1 divided by Kp. And that is intuitive because if you have a large process gain, that means you have a process that reacts very quickly. And I always like to compare this to a car. So if you have a very fast car, you go down the accelerator and you're going to increase the speed a lot because you have a large process gain. If you have a little score, like a little slow car, I don't know, a little Corsa or something, you will have to push it a lot. So it makes sense that the controller gain is inversely proportional to the process gain. Okay. And now don't be too scared. Now we're getting some crazy numbers, and they're not crazy. Obviously, this O stands for optimization. So they're optimal numbers. They're optimized, I think, over 144 different processes, simulation of 144 different processes that are common in the process industry. So this is why it's so powerful. This is why it's such a good generic calculation. 0.15 plus 0.35 T divided by L minus T square divided by L plus T square. Close bracket. And Ti is 0.35 times L plus 13 L times T square divided by T square plus 12 LT plus 7L square. Okay. So now this looks really a little, I don't know, just not a little, but this looks quite cumbersome, and we don't really know why there's well, we can have some sort of ideas, but the exact terms why is this 0.15 and why is this 0.35? That is because it's optimized for those particular processes, and it's done over 144 processes. So this is where pop out these relationships and these numbers here. So you don't have to learn them by heart, and you don't have to remember them. You just have to remember AMIGO, and that there is a paper. Oh, I think the paper is from 2002, fairly recent. It's not old. I think it's 2002. And you have to know the method. You will find that paper if you Google the authors. They are Carl-Johan Åström and Tore Hägglund. And you will find those tuning rules. Or if you Google AMIGO tuning rules, you'll find them. You just have to know that they exist. And it doesn't matter that it's slightly cumbersome because you only have to do it once, and you can do it, you can implement these tuning rules. Yeah, so you don't have to you put them in Excel spreadsheets and you just change K, P, T, and L, and you get the updated numbers, or you do it in a different computation environment. Okay, let me just sit down again to give you the values if you have a PID controller. So you will have KP, TI, and TD. And here it looks slightly easier. It's KP is again, sorry, K, the controller gain K, again is proportional to 1 divided by KP times 0.2 plus 0.5 T divided by L. And TI is 0.4 times L plus 0.8 times T divided by L plus 0.1 T times L, and then the derivative time is 0.5 L times T divided by 0.3 L plus T. Okay. So again, not pretty, but that's not really the focus here. These are the rules. And here goes my flying cap. Now we have another rule I would like to mention. This is the lambda rule. It goes as follows. It's much simpler. It's 1 divided by KP. It's also much older. It's from the 1960s. So this is a tuning rule from the early 1960s. It's very popular in the pulp and paper industry, but it doesn't mean that it only should be used there. It's just one of these things. People know about it in the pulp and paper industry because someone's done training to different people. So for a PI controller, the controller gain is 1 over KP again, T divided by L plus a tuning parameter lambda. Oof, no, another tuning parameter. Don't stress. It's easy to find. And for the PID controller, the values are 1 divided by KP, 0.5 L plus T, divided by 0.5 L plus lambda, and the reset time is T plus L over 2, and the derivative time is T times L divided by L plus 2T. So you only have this tuning parameter lambda in your controller gain K. So now, what is lambda? Oh, can't see. I have space on this board here, but yeah, I do have some more space. So lambda is chosen depending. Is chosen depending on what kind of tuning you would like to have. So lambda can be T if you would like to have aggressive tuning. It's 2T if you want to have safe tuning, and it's 3 times T if you would like to have very robust tuning. So this is sort of aggressive to robust. And we have a fourth option, which is that lambda equals to 3L for the case of long dead times. So this is what makes lambda very powerful. We can deal with loops where L is quite long, and that basically means this last option here is for the case that L is greater than 2. Okay. So all on one board, we have recap. We've done the different tuning parameters. We looked at a process model of a step response process model with 3 process parameters, and I've given some general idea how we should adjust K, Ti, and Td, what will be the impact. And here are 2 tuning rules you can use to select your controller parameters based on your process model. Because at the end of the day, you're going to close the process, and it's going to depend on the process dynamics. So this relationship shows out that we're here. This is here. It depends on the process dynamics. This lambda tuning parameter is quite nice because it can tell us, or it can talk about the control performance requirements. Do we want to have speed? Then you're going to use lambda equals to t. Or would we like to have it to be very robust? Then we choose lambda equals to 3t. And if we have processes which are slightly different, processes with long dead times, where L is very big, or L is much bigger than t, we're going to choose lambda equals to 3L.